All right, now we're to the point. We can actually predict what happens when we take two compounds and we react them together. This is called a metathesis reaction, and in particular, we're going to be looking to see whether or not a precipitate or a solid is going to form. Now, I normally do this one in class. This particular example takes lead nitrate and potassium iodide. So here's the two solutions. Here's our lead nitrate. Here's our potassium iodide. Notice they're both clear solutions. But when you mix them together, you form this yellow precipitate. This yellow solid starts to form. It's a really, really cool reaction to look at. And I'm sorry I can't show it to you right now, but let's talk about why this occurs. All right, so for this example, let's look to see what's happening on the ionic level, on the molecular level. Let's see what happens when we put these actually into solution together. Now, normally potassium iodide and lead nitrate start out as a white solid. If I went into the lab, into the stockroom and grabbed them off the shelf, I would be grabbing this white crystals. But when I put them in water, they would dissolve. Well, how do I know that? Well, I could check the solubility table. And what this tells me, and I included just the parts for iodide and our nitrate. Nitrates like to be soluble with everything, and iodide is soluble with most things. And if we look at the insoluble section, the exceptions that we have, potassium is not listed in there. We'll get to lead here in a few minutes. So if I take potassium iodide and I put it in water, it's going to break apart. It's going to dissociate into potassium ions and iodide ions. So I'm showing the charges on each of those. Now, lead nitrate is going to do something similar. So if I put lead nitrate in solution, I form lead ions. And notice we have this 2 out here. I have 2 nitrates. So in that first Erlenmeyer flask, they had one of the solutions and it's in ionic form, and then there's a bunch of water molecules. In the other Erlenmeyer flask was a bunch of water molecules and the other ions. But what happens when we mix them together? Well, we want to see what starts to form. So let's see here. This potassium, we know that if it reacts with the iodide, it's not going to form anything because, well, that's what we started with. And if we look at the potassium and we try to react it with lead, well, those two won't react. Why? Because they're both positively charged. So what happens if the potassium comes in contact with the nitrates? Well, we would form, let's see here, potassium has a +1, nitrate has a -1, we'd form KNO3. But if we check our solubility chart, we find out that this is going to be soluble. It's going to be AQ. So I know that that's not the product that I formed. Well, let's see what else we have. Now remember, we always start by looking at the positive portion. The other positive thing we have is lead. Now that lead, we already said it's not going to react with potassium because they're both positively charged, but it could possibly react with iodide. Now iodide has a -1 charge. Oh, do you remember how to balance the charges? On this one, I'm going to need 2 iodides to balance that +2 charge. Now I can go up to my solubility chart and say, okay, iodide, soluble with most cations, and here's an exception. Lead 2 is an exception. This forms a solid. So here I've kind of written out this dissociation equations and tried to figure out what would form together. Let's try this again and make it a little bit neater to be able to show how I would write this as an actual problem. All right, so we're back to these 2 basic compounds that we're going to mix together. So this time I'm going to write it a little bit different. So I'm going to say, okay, potassium iodide is going to react with lead nitrate. Now this is a double replacement reaction. The potassium is going to come over here and react with the nitrate. Now off to the side, I'm going to watch those charges. I know that K has a +1. Nitrate has a -1. I know it's kind of hidden up there. It's a 1-to-1 ratio, so that forms KNO3. Now, if I check my chart, my solubility chart, I find out that this is going to be AQ. And then the other thing that reacts is that lead comes back and reacts with the iodide. Now, this lead is a +2 charge. How do I know that? Well, in my initial compound, it's reacted with 2 nitrates. Each nitrate has a -1. Therefore, lead must be a +2. I'm going to react it with iodide. I know iodide's a -1 because it's in group 7A, which means I need to have 2 iodides to make this react. When I check my solubility chart, I find that if I react iodide with lead 2, that this is insoluble. It forms a solid. Now, what I've written is the molecular equation, but if you look closely, so I predicted the products, I predicted the phases, but I also need to balance this equation. So let me go back and balance it really quick. I need a 2 there and a 2 there. Okay, everything's nicely balanced now. So that is the molecular equation. I predicted the products and then I balanced the equation. Next, we're going to write the ionic equation. Ionic. With ionic, anything that's a strong soluble electrolyte will get broken apart. So let's start at the beginning. I have potassium iodide. Now remember, our rule so far is that if it's AQ, it's going to dissociate. It's going to break apart. Now, we're going to come up with an exception of that later on, but for right now, that's what we go with. So Ki says AQ after it, so we're going to break it apart. Now notice there is a 2 out front, so I'm going to put 2 K pluses plus 2 I minus. That lead nitrate, PbNO32, notice it has a AQ after it. So I have Pb2 plus, now notice that 2 after the nitrates. That means that I have 2 separate nitrate polyatomic ions. So plus 2 NO3 minus goes to. Let's see here, my first product is KNO3. Notice the AQ, that means it's going to break apart. So I get 2K plus 2 NO3 minus. And then I have that solid, PbI2. If it's a solid, it's going to stay together. Now, we have a lecture coming up where I do a whole bunch of these examples in a day, and I know that that will really help you when we get to that part. So try your best right now, and again, it will get easier, especially when we get to that one lecture that usually just makes everything a little bit clearer for people. Hopefully we'll be able to do that one live. Now let's see what's the same on both sides. Let's see here, my 2 Ks are exactly the same, my 2 NO3s are exactly the same. Those are going to be my spectator ions, potassium and nitrate in this example. And then I'm going to write everything that I have left over. I have 2 I minus, I was missing a minus up there. I think I wrote it and it just didn't show up because my pen's a little cranky sometimes. Plus Pb2 plus. Now, does it matter in what order I write those two? No, this is addition. So it's just saying, hey, we have these ions, they're all in solution. But if they're in solution and they come in contact with one another, they're going to form this compound, this lead iodide. This is called the net ionic equation. Net ionic equation. So let's go back and look at the picture and see if we can really look to see what's happening once we get on that magic school bus and take a look at these. All right, so here we are back at our diagrams of those different compounds. So let's see here, let's change this to purple. So here I have lead nitrate. Now remember, lead nitrate says at the top is AQ. So that means I have lead ions and I have nitrate ions sitting in solution. In the other solution, I have potassium ions, those are the little kind of bluish ones, and iodide ions, which are the larger purple ones. So if you can imagine, there's water molecules in between everything, but here we have all these ions that are separated from one another. When those two solutions are mixed, the lead and the iodide form this solid. Look how orderly it is, how a nice three-dimensional lattice it has. Therefore, we know that's a solid. Now, we still have some ions in solution. We have our little potassiums. We have our nitrates. That's why we call those the spectator ions. They're not actually involved in the making of that solid. They just happen to be ions that are sitting and watching what occurs. So I like this. Always pay attention to pictures in your textbook because they are trying to give you a nice visual of what's occurring. So here's another problem for us to try. It says predict the reaction that occurs on mixing the following solutions. Now, because it says that they are in solution form, we know that they're going to start off as being aqueous. We know that they're both going to dissociate when we put them in water. Write molecular, ionic, and net ionic equations for the reactions that take place. And we have AgNO3. Do you remember what that is? That's silver nitrate. That's the one that gets your little brown specks on your hand. And also NH4Cl, that's ammonium chloride. And then it gives a hint at the end. Always write equations in 2 steps. First, write correct formulas for the reactants and products, then adjust the coefficients to balance the equation. All right, let's give it a try. All right, so here we have that silver nitrate and that ammonium chloride. So let me go ahead and write that first part out. We have, let's change colors again. Let's do orange. How's that show up? Oh, that looks pretty good. We have silver nitrate, and we already discussed that's going to be aqueous because it's a solution. We have ammonium chloride, which is also aqueous. Now what's going to happen is that the silver, is it going to react with the ammonium or is it going to react with the chloride? Well, we know because the silver is positive, we're going to react it with the chloride, which is negative. If I said sodium a few minutes ago, I apologize. Now that silver, we know that it has a positive 1 charge because that one is a set charge. Even though it's a transitional metal, silver is always a positive 1. Chloride, we know has a negative 1. So when those two react, it's a 1-to-1 ratio, AgCl. Now if we go back to our solubility table and we look, we find out that chloride is soluble with most cations except, and silver is actually the first one listed. So we know that this is going to be a solid. It's insoluble. It forms a precipitate. It forms a solid. Now the other thing that's going to happen is that the ammonium is going to come back and react with the nitrate. Now ammonium has a positive 1 charge. Nitrate has a negative 1 charge. It's also a 1-to-1 ratio. Now when you go to your chart solubility table and you look, you'll find out that nitrates are soluble with just about everything and there's no exceptions. So I know this is going to be a soluble product. Now let's look, let's make sure that everything is balanced. Oh, it looks like it is. What I have written here is the molecular equation. Molecular equation. Molecular equation. Let's try the ionic equation. The ionic equation, anything that's a strong soluble electrolyte, for us today, that means it has AQ written after it, is going to break apart. So does silver nitrate break apart? Heck yeah, it has AQ after it. So I have silver with a positive 1 charge, nitrate with a negative 1. How about ammonium chloride? It has an AQ after it, so yep, it breaks apart. Now remember, we leave the polyatomic ions together. So we have ammonium with its positive 1 and chloride with its negative 1. Let's look at the products. The first product is AgCl, silver chloride. Notice it says solid. Does it break apart? Nope. It's going to stay together. AgCl, and we have our solid. The other thing, ammonium nitrate, will it break apart? Well, it has an AQ after it, so yep, it sure will. We have ammonium with a +1 charge, and we have nitrate with a -1 charge. Now we need to see what's the same on both sides. Ammonium's the same, nitrate's the same. And so those are our spectator ions. We write everything else, Ag plus Cl minus goes to AgCl, which is a solid. Remember, if it's anything other than AQ, you have to show that on every line. AQs, oh, I give you a little bit of a pass on that. I probably should have you write them, but I tend to drop them myself. But if it's not AQ, make sure it's written. This is called the net ionic equation. The net ionic. All right, so hopefully that one made sense. And that is how you predict metathesis reactions.